Then Mayer went on to show that this beautiful analysis that he has done. He went on to show that how this analysis that he again did the maximum term method. He picked up that particular cluster ML star, which, and the analysis fully given here, that maximized the partition function. This is the same as the Lagrangian multiplier, but before that he showed that maximum term method is the one that works. That's the maximum term method that is sufficient in the limit of infinite size of the system, n going to infinity, total number of particles going to infinity, volume going to infinity, such that n by v, the ratio of number of particles to volume density, is fixed. In that limit, that maximum term, that distribution ML star, this distribution that maximizes, that is enough. Everything else is redundant. That beautiful analysis of maximum term method combined with Lagrangian multiplier, and he could show that ML and Z here is the Z here, which tells the weight of a cluster, that is the undetermined in the Lagrangian multiplier undetermined coefficient. Z is that undetermined coefficient. We show later that Z is nothing but the fugacity. But if it is that, then LML star equal to n, and then we get n over there v, and we get the beautiful thing which is called Mayer cluster expansion. The density is LBL ZL. So now we have a beautiful relation in terms of the cluster integrals BL, and cluster integrals are nothing but those integrals that contain intermolecular interactions. So because of the cluster integrals, we have now the connection. We have built the we made the connection with the intermolecular interactions and the way. So this is a beautiful stuff. Then he went on and to go back. So this now write the partition function about one particular distribution. So we are talking of distribution of distributions because ML gives a number of clusters of size L, and but we have picked up one particular such distribution. We call it ML star. For example, that can be in a 100 particle system. M1 can be 58, M2 can be 32, M3 can be 12, something like that, and they must add up to A. So M1 is 58, and that means there are 51 monomers. Then I say, okay, there are 12 dimers. That means 2 into 12, 24 particles in that. So 58 plus 24 is now 82. Then I have 6 trimers. So that is 18. So I will have now 100. I say I have, that's the distribution I have. That maximizes. Now when n is not 100 but billions of billions, then a distribution I pick up like that is one that is representative of the system. Then I can go and calculate the partition function. Once I know the partition function, I get the free energy, and then from this partition I get the free energy, and from the free energy I can get the pressure, which is dA dVt here, and then I can show by using this relation ML star VBL ZL, I get this thing. Okay. So now this is another such cluster expansion, which is Mayer's theory. And then the further developments is done in terms of reducible cluster integrals, because those are BL contains both chain and ring. So you have to break down into rings and chains separately and evaluate them separately. That has been done for a fairly complex number of systems, very large number of things, and so this is called reduction in terms of reducible cluster integrals, and the definitions one can do, like beta 1 is these quantities, beta 1, then this is called beta 2. Now you can see if I have only chains and rings, then beta 1, beta 2 is enough, and if I have only chains in my system, no rings like in dilute gases, then beta 1 is enough. What turned out now, beta 1 is the second virial coefficient, this becomes the third virial coefficient. That is the beauty of Mayer's theory. Now we play the same game. How many of these beta 1 in the system? I call that NL. And then how many ways I can distribute into the NL? The same omega. And then I make the product of the two, and I get a, just like Mayer partition function, another expression, which is, the story goes that while Joseph Mayer could do the earlier this derivation, he could do this thing. He was he could do things, he was stuck. He could not go to reducible cluster integral and the further development. The further development was done by his wife, Maria Goeppert-Mayer, who went on to get a Nobel Prize for his work on nuclear cell theory. So, Maria Goeppert-Mayer, whom Mayer met in Göttingen and married and brought her to Columbia University, was instrumental in many such calculations of combinatorics and difficult things. So, when does that, then one goes on and one can go on to describe the theory of condensation into in a beautiful way. That means one could use these things, and one could now get the maximum term method, and one can show from the maximum term method that these two things that one does. That maximum term method gives this ML star, what we already showed is VBL ZL, and Z is the fugacity, and BL one can show is this quantity. It has exponential scaling. Then one goes to ML, and since ML goes as BL to the power ZL, and since ML is VBL ZL, and B goes as B naught to the power L ZL. So, you combine and get B naught to the power ZL, and when fugacity changes such that Z becomes greater than B naught inverse, then you suddenly have very large clusters appearing in the system, which is shown here as a distribution of LML versus L. LML is the number of clusters of size L, and L is number of particles in that clusters. LML is number of clusters of number of particles in this size of cluster L, and that then has this beautiful Mayer's picture, is that a big large cluster appears in the system, and that is the gas liquid transition. So, this is the coexistence, this would become the liquid. So, Mayer did not quite get there, but he got the picture right. His formulation was rather extended to in many great directions, and so there is a beautiful scaling also that this is a plot depicting the distribution of cluster sizes. Then what one does, the next thing was a wonderful thing, that is a virial expansion from Mayer's theory. So, Mayer then went on to show that in a low density or large volume, he can work his theory around and show that the free energy and the partition function and the free energy and the pressure has an expansion in density, which essentially comes from these two things. One is pressure is BL Z to the power L, and density is LBL ZL. So, these are two series, this is series 1 and this is series 2. Now, I can eliminate the fugacity from series 1 and 2, and I can get a series of pressure in terms of density, and that exactly is the virial series. That was what was done by Mayer, and it is described here. So, we go now, write down the partition function, just like this is the all the binary, this is the ternary. So, these are all the binary chain, these are these things, 2F bonds, and just keep these two terms, nothing else, because this has low density or large volume limit. Then I can do so. This one is just ideal gas V to the power n. Then this is where there are how many ways I can have the n number of particles get into, that's the dimer, that is n into n minus 2 by this, and V to the power n minus 2 come out because the two integrals are here. So, it is V to the power n minus 2, and then I have other one will be 3 particles, n into n minus 1 n minus 2 by 6, and V to the power n minus 3. I am not taking that into account. So, now I can, if I take that this quantity, then I can change again origin to 1, and this becomes 1 2, this becomes 1 2, then this becomes that thing, and 1 I integrate, I get a V. So then I get this kind of thing, and n is very large, so this can be neglected. I get n square by 2 V n minus 1. Then V n minus n square by 2 and this integral. Now I define this integral as beta 1, and then I get n square beta 1 by V as this this term. Then I go and calculate the free energy from this will work as Boltzmann constant. Then I work it out. Then this is the ideal gas term. Then this is the term that coming from retaining only the chain diagram beta 1 dimer, sorry, only the dimer. And then when I do that, I found that this is the sorry, this is all the work case. This is the correction that comes to pressure, the beta 1 by 2 V, and this small v is V by n, and then you get this. This is the correction that comes out. That means pressure PV by n kBT becomes 1 minus rho beta 1 by V, and this we know now. Compare this with the Virial series, you get 1 plus B2. You will find all these calculations are done here, and this will be passed on to you. So one gets the first term of the Virial series, and that's a beautiful thing that you get now molecular expression. The important thing is the molecular expression of the Virial series, and that is in terms of the series. This would be UR. So I now have second Virial coefficient in terms of dr r square fr. So this is the second Virial coefficient, and fr is e to the power minus beta ur minus 1. So this now tells a way to do the second Virial coefficient. Now this played a very important role. This particular derivation of second Virial coefficient played an exceedingly important role, and this is the following. So now I have a second Virial coefficient which is given in terms of L3 factor. I am not too interested in that, dr r square fr, and then I have, okay, of course 4 pi and other things are there, and density. Now you are, so before this we did not have, we had forms like Lennard-Jones interaction potential, but we didn't know how to get them. Quantum calculations, they are far off and very difficult. But now suddenly I have a beautiful expression of the second Virial coefficient. So I go to Van der equation, I get this part, which will be quite nicely given by the second Virial coefficient. Now I do the temperature dependence of this guy. So I get now second Virial coefficient temperature dependence. So now I fit it. So by knowing the temperature dependence of second Virial coefficient experimentally, and knowing Mayer's expression of the second Virial coefficient in terms of interaction potential, I could now get the so this was the first time so these values of epsilon and values of sigma in the interaction potential, they came out first times were calculated by using Mayer's expression of the second Virial coefficient. So Mayer's expression of second and third Virial coefficient and fourth Virial coefficient played a very important role. People started doing a molecular microscopic theory of condensation. They get the Virial coefficient. Now they see the Virial coefficients which were introduced phenologically. The Virial coefficients were introduced phenologically because this was written down P by rho kBT, P by rho kBT, it was written at 1, the ideal gas, B2 rho plus B3 rho cube. So these are just Virial coefficients, second Virial coefficient, third Virial coefficient, fourth, they are phenomenological. This was Virial did it phenomenologically from the experimentally determined equation of state. But now Mayer told us what is B2 in terms of interaction potential. Mayer told us what is B3 in terms of interaction potential. Now I can go back, use Mayer's expression and the experimental values of second virial coefficient, temperature dependence, I can get the interaction potential. So this was the huge significance of this approach, the cluster expansion, the Mayer F function, the cluster integrals BL and irreducible constant beta 1, which you can work out, they are all done here, was to get the interaction potential. So we talk all these days the force fields, all the glory of things to computer simulations. We derive very complex systems, but the fast things came out. So the Virial series is more than 100 years old. Even at the time of Mayer, it was 40, 50 years old, but one didn't know, knew that it is coming from interaction coefficient. One can expand van der Waals equation of state and get the Virial series. But one found out that doesn't work. That means that's why actually A and B was determined, but that didn't work well because they are phenomenological. They are not robust. But Mayer's theory gave us a robust way to look into the interaction potential and evaluate, and that played an extremely important role in our development. So even today, the values of the force field that we call for argon, the sigma and epsilon, comes from these kind of things. That epsilon is 119 K. That comes from this analysis. And so, so there are certain limitations of Mayer's theory, that this is the ideal gas and this is the Mayer's. Unfortunately, if you do Mayer's theory, it kind of gives the condensation, but then it remains flat, and there are many reasons for that, and we are not going to go into that in this detail. You can get that in the book. Then there are many studies, beautiful studies that have been done. So we are talking of these finite through the Bell polynomials. The Bell polynomials are a class of generalized polynomials, very powerful polynomials, which exactly has the same form Mayer. Nobody knew, Mayer didn't know, we didn't know for many years. But the advantage is that if that is so, then there will be beautiful recursion relations which we can use now, and this is the recursion relation, Bell polynomial recursion relation, which now can be used to evaluate Mayer partition function, and that's a beautiful stuff, and you get this beautiful relation of Mayer partition. So now if we can have some reasonable cluster integrals, then we can do a good job. But the difference is that this problem remained. We made considerable progress, but we didn't solve the problem because the reducible cluster integrals are not available. Even today they are not available. Irreducible cluster integrals have been evaluated by great pain, and it works out somewhat better for many techniques are there for hard sphere kind of a system when there is no attraction. It works out reasonably well. There is a very large number of reducible cluster integral Virial coefficients has been evaluated up to 11, and that means beta irreducible cluster integrals up to beta 10 has been done by graph theoretical methods, a method the Mayer initiated, but for Lennard-Jones it has been done only up to some 6 or 7 irreducible cluster integrals. That's not enough, because when it goes to liquid phase, then all the particles become connected. So there is a kind of gel that forms, and the Mayer's theory breaks down. But we should be happy with what we have got, and these some things that done. So we'll stop here today, and there are some old articles that we wrote long time ago, and there's described in the book that the applications of Mayer partition function to the real systems, and so we stop here now.